So our intended learning outcome for this discussion is first to understand the definition and significance of pre-stress concrete design. So before we proceed on studying the course pre-stress concrete design, it's worthy to know first what is the definition of the subject or the course, and what is its significance. Why do we need to study the course pre-stress concrete design? So that is our first goal for this discussion. Second goal for this discussion is to be familiar with the advantages of using pre-stress concrete. So later on, we will see if there are any advantages of using pre-stress concrete over using other kind of material or uh, structural member. Next on the list is to be familiar with the historical development of prestressing. So before we proceed with studying on the uh, uh, before we proceed on studying the latest development on prestressing, it is worthy to know as well to look back on the historical development of prestressing so that we can see how did the prestressing industry develop starting uh, from the early developments up until the modern technological developments in pre-stressing. And then last on our goal for this discussion is to understand the basic concepts of pre-stressing. So without further ado, uh, let us go to our first goal, which is to understand the definition and significance of pre-stress concrete design. So first, let's ask ourselves, what is pre-stress concrete design? What do we mean when we say pre-stress concrete design? So obviously, pre-stress concrete design is obviously as a design subject. Design of what? A design of concrete that are pre-stress. So the subject is about designing concrete that are pre-stress. But what do we mean when we say pre-stress or pre-stressing? What is pre-stressing? What is the definition of pre-stressing? So technically, the definition of pre-stressing is to introduce internal stresses to counteract the stresses that will result from applied load. So pre-stressing has a purpose of counteracting initial stresses that resulted from the applied load from a particular member, for example. So take note of the word uh, to introduce internal stresses to counteract. So that is the key words for the definition of pre-stressing. So it is the act of introducing internal stresses which have a purpose of counteracting the currently being experienced stresses of a member that resulted from the applied load on it. So to illustrate what is the meaning of uh, pre-stressing, so let's say for example, I have here a concrete beam, simply supported beam. Let's say we have here a simply supported beam that supports its own weight. So usually we assume that the weight of the concrete beam or any member is uniformly distributed all throughout the length of the member. So let's just say that the magnitude of this uniformly distributed load that is being carried by the concrete beam, which is actually its self weight. Let's just call it W sub DL. DL stands for dead load. Usually, we designate self-weight as dead load. It is the dead loads are the usually the self weight of the member. So the magnitude of this uniformly distributed, let's just call them W sub DL. And then let's just imagine that uh, so obviously since the concrete beam carries uniformly distributed load, obviously since it's simply supported, it will have reactions here. So that is a basic knowledge. So let's just imagine that this concrete beam is made up of several concrete fibers that runs longitudinally with respect to the axis of the concrete beam. So let's just imagine that uh, this concrete beam is made of infinitely many fibers. So we will just to represent those infinitely many fibers in Tagalog, hibla, kumbaga. So let's just imagine that this concrete beam is made up of napakaraming hibla. So let's just take some of those fibers, some of those hibla. Say for example, ito. So of course we cannot uh, illustrate all of those infinitely many fibers. So let's just take some of those many fibers. So let's just take this some fibers that of made up the concrete beam. So we know that the concrete beam supports uh, its own weight with a magnitude of W sub dl, and actually W sub dl, that uniformly distributed load as well as the reactions, are external to the concrete beam. So when we say external, obviously from the word itself, it is applied to the member externally from outside. But what we are really concerned here is the stresses or the forces being experienced by the concrete beam inside. So how can we investigate those internal forces acting inside of the concrete beam? So all we need to do is cut the concrete beam. So run a cutting section uh, through the concrete beam. Say for example at the midspan of the concrete beam. So this cutting section will divide the concrete beam into two segments, the left segment and the right segment. So let's just take the left segment for us to observe, to investigate the internal forces acting on this particular cross-section of the beam. So this is the left segment of the concrete beam. So since we have cut the concrete beam, we know from mechanics of deformable bodies or from theory of structures that whenever we cut a member, there will always be internal forces that will come out. In this case, the internal forces that will come out when you cut a beam are first a vertical force called shear force, which is this. So I just indicated a subscript of dl to indicate that the shear force came from the applied uniformly distributed load that came from the dead load or the self-weight of the member. So that is one of the internal forces acting inside the beam, the shear force. Actually, the shear force is the resultant of the uh, stresses acting on this cross-sectional area. So these are the stresses acting at this cross-sectional area. And actually, that stresses is what we call, since this stress came from the shear force, usually we call these stresses that results from the shear force, we usually call this shear stresses. Although we assume usually that these shear stresses acts uniformly all throughout the cross-section. Although what we meant there is the magnitude of the shear stress that acts uniformly on the cross-sectional area is usually we meant that uniform shear stress as the shear average. Because in real life, the shear stresses acting on the cross-sectional area of a concrete beam, say for example, is not actually uniform as indicated on this illustration. So you can see that the shear stresses acting on this cross-section are not actually uniform. Actually, the largest magnitude of shear stress uh, happens on this particular location. Say for example, if we have a rectangular cross-section, usually the largest shear stress happens on the neutral axis or along the centroid of the cross-sectional area. And then as you go on the top fiber or the bottom fiber, the shear stresses diminish. So that is the reality of shear stresses. Although again, in design purposes or in analysis purposes, we usually assume that these shear stresses are constant or uniform, acting all throughout the cross-sectional area. But again, that magnitude of shear stress that we meant as constant is just the average of this non-uniform shear stresses. With the largest or with the maximum shear stresses acting or occurring at the neutral axis. So that is one of the internal forces that will come out when you cut a beam. Another internal force, or actually this is not a force, it is a moment. Another internal moment that will come out when you cut a beam is what we call bending moment. So again, I just indicated the subscript DL dead load to indicate that this bending moment came from the applied uniformly distributed load that came from the dead load or the self-weight of the member. So again, this internal moment acting on this cross-section is actually the resultant of the, the stresses acting on this cross-sectional area. Actually, those stresses are what we call flexural stresses. So, uh, if you will sum up those flexural stresses acting on this cross-sectional area, you will see that their resultant moment is this magnitude bending moment. So to give you an idea, does those what does those what does those what do those inter flexural stresses look like? Say for example, uh, let's imagine what will happen to this concrete beam if it supports this uniformly distributed load. So if you can imagine what will happen to this concrete beam as it supports this kind of uniformly distributed load, the concrete beam tends to bend with a shape of concave upward. If you can imagine that, if this concrete beam will support this uniformly distributed load, tendency it will bend like this one, concave upward. And if you will investigate what will happen on this originally horizontal fibers of the concrete beam, you can see that they have they had deformed. They had deformed. Actually, you can see on this figure or illustration that the fibers on the top part of the concrete beam actually experience shortening, while the fibers at the bottom part of the concrete beam experience elongation. And actually, there is a part here, there is a fiber here along the beam that neither experience shortening or elongation. And actually, that part of the concrete beam that that did not deform is what we call the neutral axis if we are talking about the two-dimensional space, the cross-sectional area, or if we will look at the three-dimensional uh, figure, that line or that fiber that did not experience deformation is what we call neutral surface. Neutral surface. So it did not uh, either shortened or elongated. So the fibers above this neutral surface, like this one, the fibers above the neutral surface, experience shortening. And we know for a fact that when a material shortens, obviously there is a compressive force or compressive stresses that that is the reason why it experiences shortening. So meaning the flexural stresses that is being experienced by the fibers above the neutral axis or the neutral surface points directly towards the concrete, and it compresses the concrete cross-sectional area like this one. So the flexural stresses above the neutral surface or the neutral axis points toward the concrete because the stresses or the flexural stresses acting on that part compresses the concrete. As a result of that compression, the fibers above the neutral surface experiences shortening. And on the other hand, the fibers below the neutral surface experience opposite effect. So instead of shortening, as you can see on this figure, the fibers experience elongation. So again, if a material experiences elongation, therefore, it experiences tension or tensile force or tensile stresses. And we know for a fact that tensile stresses points away from the member. So those tensile stresses look something like this. So they point away from the material. These stresses above the neutral surface or neutral axis points toward the material, therefore it compresses the member. And then these stresses below the neutral surface or neutral uh, neutral axis points to outward or away from the concrete or the material. Therefore, it imposes tension or tensile stresses. So if we will connect those flexural stresses being experienced by the material at this particular cross-section due to bending, due to the application of this uniform distributed load, it will look something like this. This is the diagram. So actually, theoretically, we assume that this stress at the outermost top fiber and the stress at the bottom fiber are equal. So you can expect that uh, we have a linear variation of stresses on this cross-sectional area. So those stresses, if you will find the resultant of these stresses, obviously their resultant force is equal to 0 because uh, this force and this force are just equal. So the resultant force is equal to 0. But if you will observe, this force and this force produces what we call a couple moment because they have same magnitude, parallel, same magnitude but opposite in direction. Actually, all of these stresses produce what we call couple moment, and actually the resultant of those many couple moment is actually this bending moment. So if you can imagine the couple moment being produced by this stress and this stress points or has a direction counterclockwise, same as this. So that is what I have meant when I said a while ago that this bending moment is actually the resultant of this flexural stresses. We call this flexural stresses because it tends to bend the concrete beam. So that is the stresses, shear stress and the flexural stresses being experienced by the concrete cross-section at this particular section at midspan, say for example, due to dead load only. But if you can imagine, if we will add additional load to the concrete beam, say for example, uh, the concrete beam already carries the what we call superimposed dead load. So therefore, we have additional load to be carried by the concrete beam, and due to that additional load, again, there will be additional internal forces and moments that will be produced inside the concrete beam. So let us just call the bending moment resulting from the additional superimposed dead load as M sub SDL. bending moment due to the superimposed dead load, and let's just call the resulting shear force due to the additional load SDL. Let us just call the additional shear force resulting to that SDL as VSDL, shear force due to the superimposed dead load. So if you will observe here, the bending moment acting on this cross-section increase, because a while ago it's just MDL, now it is MDL plus MSDL. So the bending moment increase, therefore the resulting flexural stresses due to this bending moment will also increase. So you can imagine that these magnitudes will also increase. So mag-ano siya, it will elongate, or I mean it's dito sa figure natin, sa diagram natin, you can imagine yung height or length nitong mismong pressure diagram na to, lalaki siya. Kasi lumaki yung yung bending moment natin. So medyo I did not change the diagram anymore. Hindi ko na siya pinahabaan to show that the flexural stresses increase. So just imagine that these flexural stresses increase because there is an additional bending moment. And again, if the concrete beam will have additional load to be carried, say for example, the load due to the live load that is intended to be carried by the concrete beam, just like what happened on the SDL, the superimposed dead load, there will be again resulting additional bending moment and shear forces due to the application of the uniformly distributed live load. And again, since the bending moment increase, again obviously the flexural stresses will increase. So this magnitude will increase, this magnitude will increase, and so on. So let us just call the flexural stress acting on the topmost fiber as F sub T, flexural stress at the top. So I indicated negative because just like what I have said before, the stresses acting above the neutral axis or the neutral surface are compressive stresses, and usually we usually assign a negative sign to indicate compressive forces or compressive stresses, while for tensile stresses or tensile forces we usually indicate a positive sign. And obviously the flexural stress at this bottom fiber is obviously tensile, so it must have a positive sign since it points outward away from the concrete beam. So let us just call that particular magnitude of flexural stress acting at the bottom of the beam as F sub B, flexural stress at the bottom. So again, positive because it is tensile. So these are the flexural stresses acting on the concrete beam as it carries the intended loads that it is supposed to carry. So habang tumataas yung load that the concrete beam carries, the flexural stresses being experienced by these infinitely many fibers also increases. Habang tumataas yung load na kinikerry ng concrete beam, yung flexural stress, compressive stress dito sa top fiber, and yung tensile stress acting on the bottom fiber also increases proportionally. But if you can remember, concrete is strong to resist compressive stresses but has a little strength on resisting tensile stresses. Actually, the tensile stress, the tensile strength of concrete beams is usually ranges from 8% to 14% of FC prime, which is the 28-day compressive strength of concrete. So you can see that the tensile strength of concrete is just a very low or very small portion of its compressive strength. The 28-day compressive strength just ranges from 8% to 14%. That is a very low value. That is a very low tensile strength. So say for example, since this is a tensile stress acting on the concrete, say for example, if we assume that the magnitude of that tensile stress acting at the bottom part of the concrete beam will exceed the tensile strength of the concrete. What will happen? What will happen if that flexural stress or tensile stress acting at the bottom of the concrete exceeded the tensile strength of the concrete? So tendency, cracks will develop. Cracks will develop starting from the bottom of the uh, concrete beam, and then it will easily propagate and up to the topmost fiber of the concrete beam. Why? Why will it? Why will a crack will easily propagate up to the topmost fiber of a concrete beam? Because we all know that concrete is a brittle material. So when we say brittle material, it has a sudden failure, meaning uh, even if we have a little crack there, since concrete cannot resist tensile stresses larger than this tensile strength we have here, therefore uh, it will break or it will fail. So cracks will form and will look something like this. So cracks will form starting from the bottommost part where the tensile stress exceeded the tensile strength of the concrete, and then it will easily propagate up to the topmost fiber of the concrete, therefore resulting to failure of the concrete beam. So you can imagine that the the concrete beam will be divided into two segments, left segment and right segment. They will break off if cracks will develop at the bottommost fiber. Now, fortunately, if we have a what we call reinforcing steel that is placed at the at this lower portion of the beam, the tendency is that if the tensile strength of the concrete beam is exceeded, therefore cracks will already develop. As the cracks propagate to the upper portion of the concrete, when it reaches the location of the reinforcing steel, the tendency is the tensile stresses being experienced by the concrete on that portion will be uh, uh, placed, will be transferred from the concrete to the reinforcing steel. So instead of yung concrete pa yung nagre-resist ng tensile strength or tensile stress, pagdating nung cracks dun sa sa location of the reinforcing steel, the tensile stress will be transferred from the concrete to the reinforcing steel. Therefore, the cracks will be stopped to propagate. So hindi na magkakaroon ng ng sudden failure if we have reinforcing steel. That is the case on reinforced concrete design. Meron tayong reinforcing steel na nilalagay dito sa bottommost, sa may bottom part, malapit sa bottom part ng na concrete beam natin. So so our goal is to prevent this scenario kung saan cracks will develop and eventually will cause failure to the concrete. To prevent that scenario to happen, our goal is to minimize, if we cannot totally eradicate, the tensile stresses developed on this bottommost fiber of the concrete beam when the service loads are applied. When we say service loads, these are the live loads and the dead loads. So usually the dead loads is composed of this dead load that came from the self-weight of the member and the superimposed dead load. Yung mga dead load na pinatong lang. That's why it's called superimposed. So that is our goal. Kasi we know for a fact na kaya nga nagka-crack. Kasi nga, yung tensile stress na to, yung F sub B na yan, exceeded the magnitude of the tensile strength of the concrete. So, ang gusto nating mangyari, yung tensile stress na yan being experienced by the concrete beam as it supports these service loads will be minimized, will have a value less than the tensile strength of the concrete so that there will be no cracks that will develop, and if there will be no cracks, there will be no failure. So that is our goal. So how can we minimize this tensile stress acting on the concrete beam? How can we minimize that? If we cannot totally eradicate that, how can we minimize that? So that is one way to eradicate that or minimize that tensile stress is to put a pre-stressing reinforcement. Take note of the word pre-stressing reinforcement. It's not steel reinforcement, just like in reinforced concrete design. It is what we call pre-stressing reinforcement. So later on, you will know more about this pre-stressing reinforcement. So one way to uh, minimize the tensile stress, this tensile stress being experienced by the concrete beam, is to put a pre-stressing reinforcement on the concrete beam that will impose what we call compressive force, just like that, those two, that will impose compressive force to the concrete beam. That is one way to minimize this tensile stress. We can put a pre-stressing reinforcement there that will impose a compressive force just like that on the concrete beam. So what will be the consequence of having this pre-stressing reinforcement? So if we will look back to the left segment of the concrete beam, which is this. So a while ago, the free body diagram of the left segment looks like this. But since we have added a compressive force P, there will now be a compressive force P here. And for equilibrium, if we have a horizontal force pointing to the right, there must be a horizontal force as well pointing to the opposite direction in order to resist or to balance this force. So, saan manggagaling yun? Where will that compressive force will come from? Obviously, on this cross-sectional area. So, there will be a internal compressive force that will act on this cross-sectional area in addition to this internal forces, shear forces, and bending moment. And just like the bending moment and the shear forces, this actually we can call this axial force because obviously according to the drawing or the figure, it acts along the axis of the concrete beam. So we can call this axial force. So just like the bending moment and the shear forces or the shear force, this axial force also produces stresses on this cross-sectional area. So just like shear force, which produces what we call shear stresses on this cross-sectional area, and just like bending moment that produces flexural stresses on this cross-sectional area, this axial force also produces stresses on this cross-sectional area. And actually, the magnitude of that stresses being imposed by this axial force on this cross-sectional area is usually assumed to be uniform, just like this one. If and only if this axial force acts on the centroid of the cross-sectional area, which is the case here. So we can assume that the stresses that this axial force produces on this cross-sectional area is uniform, just like this one. So let's just call the magnitude of that axial stress that came from this axial force. Let's just call that uh, F sub P. So stress that came from the axial force P. And again, since this force points towards this concrete beam, so obviously it produces compressive stresses. So that's why I indicated here negative to indicate that these stresses are compressive stresses. So what will be the purpose of these compressive stresses that resulted from this from the application or from the addition of pre-stressing reinforcement to the concrete beam. What is the purpose of that? The purpose of that is to actually again minimize this tensile stresses. Like for example, since in this case the flexural stresses here in this figure came from the dead load only. Say for example, if we will add additional load to the concrete beam, just like what happened before, there will be again additional moment due to that additional load as well as additional shear forces. And again, if we will add again additional load to be carried by the concrete beam from the live load, for example, there will be again additional bending moment and shear force that will result on that additional live load. So again, you can see that the bending moment increase, so there will be again corresponding increase on this flexural stresses. So again, just like before, let's just call those flexural stress resulting from the dead load, superimposed dead load, and live load as F sub T for the topmost fiber and F sub B for the bottommost fiber. So these stresses are just the same from the previous example. So that the only difference is that if before the only flexural stresses being experienced by the concrete beam uh, is this that came from the bending moment alone, now since we added pre-stressing reinforcement, we now have additional stresses that came from the compressive force, that came from the additional or that came from the addition of pre-stressing reinforcement. So if we will get the resulting flexural stresses that acts along the fibers of this concrete beam, resulting from these flexural stresses as well as this compressive stress coming from the compressive force from the pre-stressing reinforcement, if we will add them, the figure will show something like this. So if you can imagine, if this is the cross-sectional area of the concrete beam, if we will add this stress to this stress, and then add this stress to this stress, add this stress to this stress, and so on, the diagram will look something like this. So we have this stress pointing to the left since it is compressive, and then we will add the magnitude of this compressive stresses as well. So dadagdag lang siya dito sa mga uniformly distributed stresses na to. So the diagram will look something like this. If we will add this upper portion with respect to neutral axis. But if we will add the stresses acting below the neutral axis, since the stresses have opposite direction, they will counteract each other. So if we will add them, there will be a subtraction actually, that not addition, there will be a subtraction of stresses. So like for example, if we will add this stress to this stress, obviously the resulting stress will be a stress pointing to the right kasi mas malaki ito eh. The magnitude of the stress here is bigger or larger than this stress. And so on. If we will add these corresponding stresses, the diagram will look something like this one. There. So as you can see, as I mentioned before, the sum of this stress and this stress will be pointing rightward because this has a larger magnitude according to this diagram, according to the illustration. So if we want to find the actual magnitude of this stress acting at the topmost fiber of the concrete, so actually that stress will just come from the sum of this stress that came from the bending moment and this stress that came from the axial force. So therefore, their sum will be negative Ft plus negative F sub P. So let us just call their sum as F sub T prime, the flexural stress at the topmost fiber after addition of pre-stressing reinforcement. While on the resulting stress at the bottom due to these flexural stresses and these axial stresses will have a magnitude of F sub B plus negative F sub B. So again, let's just call those the sum of F sub P and F sub P as F sub B, the flexural stress at the bottom, after the prime, the apostrophe indicates after addition of pre-stressing reinforcement. So by observing on this diagram, we can see that when we added a pre-stressing reinforcement to the concrete beam, originally the flexural stresses on the concrete beam looks something like this lang, ganito, 'di ba? Yung kanina, ayan lang yung flexural stresses kanina nung wala pang pre-stressing reinforcement. So the magnitude of the tensile stress acting at the bottom fiber has this magnitude, F sub B. But when we added a pre-stressing reinforcement, the magnitude of the tensile stress acting at the bottommost fiber is now this. So obviously, if we compare this to this stress, originally the flexural stress at the bottom of the fiber before the addition of the pre-stressing reinforcement, if we will compare this magnitude and this magnitude, obviously, this magnitude of tensile stress is obviously less than this magnitude of tensile stress acting at the bottom of the concrete beam before the addition of the pre-stressing reinforcement. So therefore, when we pre-stress the concrete beam, the tendency, the result will be, we have minimized, yan o, obvious naman sa diagram, di ba? We have minimized the tensile stress acting or being experienced by the concrete beam. Kanina, ganito kalaki yung magnitude ng tensile stress at the bottom fiber. Pero since we added pre-stressing reinforcement, ang tensile stress na lang sa bottom fiber ay ganito na lang kalaki. So, lumiit siya. We have minimized the tensile stress acting at the bottom fiber of the concrete beam by adding a pre-stressing reinforcement, or should I say, we have minimized the tensile stress acting at the concrete beam when we pre-stress it. Nung pinistress natin siya, lumiit yung tensile stress at the bottom. So tendency, since we have minimized the tensile stress acting on the concrete beam, we are sure that there will be no cracks kasi obviously this magnitude is less than the FT kasi 'di ba sabi natin kanina, this FB FB is greater than dun sa tensile strength na nung concrete beam. That's why nag-crack kanina. Pero ngayon, since limit na yung tensile stress dun sa bottommost fiber ng concrete beam, obviously wala nang crack. There will be no cracks to develop. Kasi FB will now be less than FT. Yung stress, the stress at the bottommost fiber will now be less than the tensile strength of the concrete. So there will be no anymore cracks that will develop on the concrete beam as it supports the service loads when we added a pre-stressing reinforcement. So actually, additional result other than minimizing the tensile stress being experienced by the beam at the bottommost fiber, other than that, actually, addition of pre-stressing reinforcement actually also increases the capacity of the concrete beam. So kung kanina, nung dinadala ng concrete beam yung service loads na to, ang tensile stress na nararamdaman niya at the bottom fiber ay ganito na kalaki. Pero ngayon, since nag-add na tayo ng pre-stressing reinforcement, ang tensile stress na lang nararamdaman niya sa bottom fiber ay ganito na lang kaliit. So, ibig sabihin lang yan, malayong malayo pa siya sa tensile strength niya. Meaning, it is far from cracking pa. Ibig sabihin, hindi pa siya magka-crack habang dinadala niya tong service loads. Ibig sabihin, we can still apply additional load dito sa concrete beam. Assuring na kahit na mag-apply tayo ng additional load dyan, obviously, this stress will not be approach the tensile strength of the concrete. Say for example, we have applied additional load here. Yan. So obviously, because we have applied additional load, obviously, there will be additional bending moment and shear force due to that additional load. So again, since the bending moments increase, again, these flexural stresses will also increase. So if those flexural stresses will increase, say for example, ito, lumaki siya, if this flexural stress will increase, obviously, this resultant tensile stress at the bottom of the bottom fiber of the concrete will increase as well. But we are sure that it will not approach anymore to the tensile strength of the concrete. Ibig sabihin lang nun, what I just want to say is, kahit magdagdag tayo ng additional load dyan, since eto na lang yung tensile stress na nararamdaman ng concrete, which is far from the tensile strength of the concrete, kahit magdagdag tayo ng additional load dyan, at lumaki pa yung flexural stresses na to due to the additional bending moment, we are sure na medyo hindi pa yan naabot sa tensile strength ng concrete. So, ibig sabihin lang nun, due to the addition of the pre-stressing reinforcement, nagkaroon ng additional capacity yung concrete natin. Kung kanina, buhat-buhat niya lang to, tapos ang naramdaman niya na tensile stress dito ay halos FT na, greater than na sa FT, kaya magkakrak na siya. Ngayon, since nag-add tayo ng pre-stressing reinforcement, eto na lang yung tensile stress sa kanya, meaning kahit magdagdag tayo dyan ng additional load, at lumaki pa yung bending moment dyan, and then resulting to that additional bending moment, lalaki pa tong tensile stress dito sa bottom fiber. Kahit lumaki yan, pag dinagdag natin yan dito sa effect nitong compressive force na to, we are sure na kung lalaki man yan yung tensile stress na yan, we are sure na medyo it will be far from the tensile strength of the concrete. Or pwede, umabot siya dun sa tensile strength ng concrete hanggang sa mag-crack na siya. Pero, sabi ko nga, bago mo siya mapag-crack ngayon, since may pre-stressing reinforcement na siya, bago mo siya mapag-crack, bago mo siya mapaabot dun sa tensile strength niya, kailangan mo pa magdagdag ng additional load. Ibig sabihin lang nun, we have increased the capacity of the concrete beam. Kung kanina, ito lang kaya niya, nag-crack na siya, ngayon, kailangan mo pa magdagdag ng ganitong magnitude ng load para mapag-crack mo siya, para umabot siya dito sa tensile strength niya. So therefore, the capacity of the concrete beam increase. Ibig sabihin, nadagdagan yung capacity niya, nadagdagan yung kaya niyang i-resist na bending moment, as well as the shear force. Actually, pati yung torsional strength niya nadagdagan, although we cannot show here the torsion part because medyo two-dimensional lang tayo. Pero later on, we can see that due to the pre-stressing reinforcement, the capacity of the concrete beam with respect sa bending moment, shear, and torsion are increased. And then, actually, yung pre-stressing, the pre-stressing what we did here is actually called linear pre-stressing. Yung addition natin ng pre-stressing reinforcement dito, that kind of pre-stressing is actually called linear pre-stressing. So why is it called linear pre-stressing? Because the pre-stressing force is applied parallel to the axis of the member. So obviously this is the pre-stressing force, and obviously it is parallel to the axis of the member or the concrete beam. So if that is the case, we can say that this pre-stressing is actually a linear pre-stressing. So syempre kung may linear pre-stress, if we have linear pre-stressing, meron ding tinatawag na hindi naman non-linear. So later on, I will say kung ano yung other type of the pre-stressing. So kung may linear pre-stressing, which is this case, meron ding ganitong case. Say for example, we have here a wooden stave. If you are familiar with that, it's like a old type barrel. Old type barrel, yung composed of parang mga mga pira-pirasong planks. Ayan, yung mga pira-pirasong planks na yan. Kung nakakita na kayo ng barrel, if you have seen a barrel or wooden stave, di ba yung walls niya, it is composed of many parang planks na pinagdikit-dikit lang, or minsan meron siyang nakaikot dito na na parang steel band. So kunyari, ito ay isang wooden stave that has a fluid inside, say for example a water. So if we will investigate the effect of water, of the water contained on this tank or barrel to the walls of the barrel, so we have to cut the barrel into sections or into segments so that we can investigate the internal forces acting on the wall. So if we will cut the barrel using this section plane, it will look something like this. So to water yung laman niya sa loob, and then yung kulay blue, that is the wall of the tank or the barrel. So ano ba yung effect nung laman na to na water dun sa wall ng tank or wall ng barrel? So the water contained inside the barrel imposes what we call pressure, internal pressure to be specific, to the walls of uh, the the barrel or the tank. So let's just assume na the magnitude of those internal forces are constant all throughout. If you can remember this topic, actually, this is similar to the topic on the mechanics of deformable bodies or fluid mechanics, the circumferential stress or the tangential or longitudinal stress. This is same on those topics. So the effect of the water contained inside the barrel is it pushes away the wall of the tank or the barrel, the wooden stave. So the tendency, if you will investigate the components of this pressure, the the vertical component of this force and this force, and the vertical component of this force and this force, and the vertical component of this force and this force, and so on, uh, cancel out each other. Kasi ito, yung vertical component nito, ito na lang kanyari, yung vertical component nito, di ba, obviously pointing upward, ito pointing downward. Since equal yung magnitude nila, obviously they have equal y component or vertical component. And since opposite yung direction ng mga vertical components nila, if we add them, they will just cancel out each other. So meaning, ang matitira na lang is yung horizontal component. Yun lang yung unbalance dito. So who will resist those horizontal components here? Magre-resist ng mga horizontal components ng pressure na ine-exert nitong water sa wall ng tank ay yung tinatawag natin niya tangential stress acting on the wall of the tank or the barrel. So if you can remember that tangential stress on mechanics of deformable bodies or fluid mechanics, that is the force that will resist the horizontal component of the pressure acting inside the barrel or the tank. And that is obviously a tensile force because it points away from the wall. So again, if you can imagine, especially if this is the case kung saan the wall is composed of several components na pinagdikit-dikit lang, if there are tensile forces or tensile stresses acting on those pinagdikit-dikit na members, tendency they will break out. So pag nasira sila, tatagas yung tubig. So one way to further strengthen this wooden stave is to put prestressing force on it. Say for example, by adding a what we call steel band. So if we will look at that steel band here, it will look something like this. Oh, nag-alarm pa ako. The steel band will look something like this. And if this is pre-stress, that steel band will impose another tensile stress in terms of the wall. It will impose pre-stressing stress, obviously, that will help this tangential stress to resist the horizontal components of the pressure acting inside the tank or the wooden stave or the barrel. So that this kind of prestressing, wherein the prestress force or the prestress acts tangent to the member, that kind of prestressing is what we call circular prestressing. So if we have linear prestressing, we also have circular prestressing. So what is circular prestressing? Circular prestressing is obviously prestressing wherein the force is applied tangent to the axis of the member. So if this is the member and this is the prestress, obviously according to this diagram or according to this figure, this prestress is acting tangent to this member, to the axis of this member. And take note, the members of this wall are composed of many wooden planks, if it is called wooden planks. So those are the two types of prestressing: linear prestressing and circular prestressing. So we are done with our first goal for this discussion. We already defined and have known the significance of prestressed concrete or prestressed concrete design. So check na tayo dyan. So now, let us go to our second goal for this discussion, which is to be familiar with the advantages of using prestressed concrete. So now, let's look if there are any or there is any advantage on using prestressed concrete.